Okay, welcome back everyone. In this last segment of our videos on magnetism, we're going to be talking about Ampere's law as applied to solenoids and toroids, and then we're also going to be talking about a very important concept called displacement current. So first of all, let's imagine a solenoid, which got a little bit cut off here but has a voltage source at the bottom here. Because of this voltage source, we're going to have a current I, which goes through each of the loops of this solenoid. So this animation is a little annoying, but we want to show that the magnetic field has magnitude B equals mu naught I naught N. Now N, let's go back. N is basically the number of loops per unit length. So if the solenoid has a length of L, then little n is basically loops per meter. That means that the total number of loops will be n times L, loops per meter times meters. Now this is going to help us calculate how much current we have, because each wire is going to have I naught going through it. Think about a series circuit. Every part of the circuit has the same current. So Ampere's law tells us that the integral of B dot ds along an Amperian loop is equal to mu naught times I enclosed. Now we have a couple things that we need to figure out. The first thing is, what is our Amperian loop going to look like? Well, we can't really go in a circle around it like we did before, because that's not what the magnetic field is going to be doing. If you think about the right-hand rule, as the current is sort of going through this loop right here, that's the current, the magnetic field is going to be kind of looping around that. So really what's going to happen is that the magnetic field is going to be going like so, along the long axis of the solenoid. And we're also going to make the simplifying assumption that the magnetic field is actually equal to 0 outside the solenoid. Now you may wonder why we can do this. It turns out that it's not exactly 0, but the more tightly packed these loops are together, the closer. So we're just going to make that assumption. Now what does our Amperian loop look like? Well, it's actually going to be not a loop so much, it's going to be a rectangle. Okay, so this is our Amperian loop. We're going to stick that right inside of that solenoid. Okay, so how much current does that loop contain? Well, up at the top here, we're going to have that first wire, and then that second wire, and the third one, and the fourth one, all the way. So we're really going to have N is equal to NL loops of wire that each carry I naught. So for that reason, I enclosed is going to be NL I naught. And that's going to help us. So now we think about our loop. When we travel all along the loop, the only time that we pick up our line integral is when we're inside of the solenoid. And so the entire line integral of B dot ds can be boiled down to B times L, the long axis of the loop. So think about this. Even though we have 4 sides to this loop, we don't even know what this side is and this side is. It doesn't matter because there's no field that we're going along, and we're not enclosing any charge, any current going that way. The right side will therefore be equal to mu naught I enclosed, which is N L I naught, and L is going to cancel out to give us a field equal to mu naught I naught N, which is what we set out to do. In our next example, we're going to do the magnetic field of a toroid. So this is a toroid, and basically what this is that you have a bunch of wires where current is going into the page and a bunch of wires where current is coming out of the page. And these are separated by some distance. So we really have three loops that we can draw. We can draw an inner loop right here, loop 1. We can draw a loop in between these, so we'll call that loop 2. And actually we'll go this way just for fun. We'll go clockwise. You'll see why in a second. And we can draw another loop out here. We'll call that loop 3, and we'll call that loop 2. Now, the magnetic field of 1 and 3 is going to be equal to 0 because the current enclosed by each of those loops is 0. And we're just going to assume that for every x we have a dot, so that for 3 the x's and the dots cancel out. It's kind of like plus q and minus q for concentric shells. If I have plus q and minus q, it's going to add up to 0. But then in region 1, that's easy because there's nothing in the middle there, so it's not enclosing any charge. It's only going to be region 2 that's going to be interesting. And for that, we're going to set up Ampere's Law. So we're going to have the line integral of b dot ds is equal to mu naught I enclosed. Now what's I enclosed for this setup? Well, each of these wires has a current I naught, and there are capital N of them. So that means it's just mu naught N I naught. Now the left side, we think about our loop, and we think about what our magnetic field is doing. So if you point your thumb into the page, then you're going to see that the magnetic field is actually going to loop around in this direction. And because of this, we are going to be able to calculate the value of the magnetic field pretty easily. It's going to be B, whoops, too far, B times 2 pi r, where r is the radius of that second Amperian loop. Okay? So this means that the magnetic field is just going to be mu naught rather, big N I naught over 2 pi r. Now there's one simplification that we can make here. If the x's and the dots are relatively close together, so in other words, if this distance here, call it delta r. Okay, if delta r is pretty small compared to r itself, and we can discuss how small it has to be. But if that space is small, then we can essentially say that the number of loops is equal to little n times big L, okay? And L is going to be basically equal to 2 pi r, okay? And so we can substitute that this is going to be equal to mu naught, and big N is going to be NL and I naught over 2 pi r. And then we recognize that L and 2 pi r are the same. So actually, it almost looks like the magnetic field of a solenoid. So that's another little trick that we can do for a toroid, depending on the geometry. Okay, now the last topic that we want to cover is the concept of displacement current. And this is something that came up when Maxwell was writing his equations, and he realized that there was a bit of a problem. So you have to imagine that you have two capacitors, the red and the blue, and you have a current IC that is what's known as a conductor current. Okay, so IC is the conductive current. We're going to say that there's such a thing as a displacement current. That's going to be ID. And here's why we need to have a displacement current. So that's ID. Between the capacitors, there's no physical current, but there is a changing electric field, because what happens is as IC proceeds, current piles up on the plate. Because of this, an electric field goes across the plates. But according to Ampere's law, there's two surfaces here. This circle, and then this weird bulging surface. But both of them are bounded by the same Amperian loop. And that's the path that we use for Ampere's law. Now, because those loops enclose or bound the same surface, then we need to have the same current on both sides. So we need to have basically I is equal to IC plus ID. And it turns out that on the left here, the displacement current is 0, and on the right here, the displacement current will be equal to something that causes us to have non-zero total current. So how do we think about this? Well, we modify Ampere's law so that displacement current is contained within the last term. So IC here is conduction current, so mu naught times I total is actually equal to mu naught times I conduction plus I displacement. And these really should be lowercase because they're as a function of time. So how do we get this expression here, epsilon naught d phi dt? Well, just remember that the charge on a capacitor Q is equal to CV. That's a V for voltage, but it's changing. And a parallel plate capacitor is epsilon naught A over D times the voltage. And also on a parallel plate capacitor, the voltage is the electric field times the distance that we travel. So that cancels out. And what we get is that this charge is equal to epsilon naught E times A. Now you might remember from earlier in this chapter that B times A was magnetic flux, and E times A is what we call electric flux. Which makes sense because you have electric field lines going through a surface. So that's the charge, and how do we get to current? Well, current is just dq dt. So we take our expression for charge, epsilon naught phi, and we take the derivative of that with respect to time. And then when that's multiplied by mu naught, that's going to give us our displacement current. Now, some of you who are advanced students or have studied this may recognize that mu naught epsilon naught is a very, very important concept. And we'll talk about how important a little bit later on, but it's very interesting that it pops up in this displacement current term. Okay, so that wraps things up for magnetism. And in our last unit for AP Physics C, we're going to be studying electromagnetism. So what are the links between electricity and magnetism? How do electric fields induce magnetic fields and vice versa? And then we'll be talking about different types of circuits, such as RL, LC, and LRC. So we'll see you next time.